In this video, we're going to look at another way to put together our basic functions to construct more interesting functions. Consider the example of trying to define addition. So this is the function add, which takes two inputs and gives us, of course, x plus y. So it takes an x and a y and gives us x plus y. But the problem, of course, is that this symbol is not defined in our primitive recursion world. Not defined. So how can we define this? Well, what do we have? We know we do have the successor function, of course, which is the function that we give it an x and it gives us an x plus 1. So maybe we could use this to help define this. So for example, we could say something like this. Add of x and y plus 1 is the successor to add of x and y, right? So let's look at an example of that just in case that's not clear. So add of 3 and 2 is equal to the successor of the addition of 3 and 1, which is equal to the successor of add 3 and 0. And now we reach this interesting case where we're adding 0 to a number, and what happens when we add 0 to a number? Well, we just get that number back, right? So this is just going to be equal to successor of 3. Okay, so this is looking quite a bit like a recursive function. Okay, so our base case here is this 0 case, right? We're adding 0 to a number and we just want to get that number back. That's our base case. And our recursive case is, what's that going to be? Well, that's what we had before. It's when we have an x and we're adding something to it. We're going to add y plus 1 to it, and that equals the successor of the sum of x and y. Okay, and this base case, recursive case, is the sort of fundamental formula for recursion, right? So let's look at a construction now that's going to allow us to express this within the primitive recursive functions. So we're going to look at primitive recursion. What primitive recursion does is it takes an f, which is going to act as our base case function, and this function takes n inputs and gives us a single output. Then it takes a g. This is going to act as our recursive case function, and this takes n plus 2 inputs and gives us a single output back. And we'll see why we say it takes n plus 2 inputs in just a second. Then finally, we're going to define, using this construction of primitive recursion, an h, which is going to be equal to the primitive recursion with our base case function and our recursive case function. And the way we define that is we say this row symbol here, and we use this number here as the parameter to our row, and we say f and g. So this is h is the primitive recursion with base case function f and recursive function g. And this is a function from n plus 1 inputs to a single output. And again, we'll see why this is n plus 1 in just a second. Okay, so f is our base case. Let's not draw an arrow there though. Let's define h piecewise. So let's say h takes n plus 1 inputs, so we'll give it n inputs to start off with, and then 0 is its final input. This is the base case that primitive recursion always considers. So in this base case, we're just going to pass on these n inputs to our base case function f. Right? That's simple. I'll label this base case. In our recursive case, we do something a bit more interesting. What we're going to do here is, so again, h takes n plus 1 inputs. We'll give it x1 up to xn. And then its final input here, of course, isn't 0 because we're not in our base case anymore. So it takes a final input, we'll call it y plus 1. And what we're going to do, or what primitive recursion is going to do, I should say, is it's going to pass some inputs to g. So what's it going to pass to g? It's going to give it the first n inputs, and then it's going to give it y. Notice not y plus 1, it's going to give it 1 less than the final input. It's going to give it y. And the final input to g is going to be a recursive call to our recursive h function. Okay, so that's going to be x1 up to xn, and the last input there is going to be y. So notice here we had x1 to xn and y plus 1, and here we have x1 to xn plus on the end we have the y. So we're kind of going to whittle this down one way or another so that the final input here tends towards 0, and eventually we hit this base case. Okay, so that's why g takes 2 more inputs than f, our base case function, because the 2 extra inputs it takes are the final input to h and the recursive call. Okay, so this can look a bit scary at first, so feel free to stare at this definition for a second, and let's look at some examples of primitive recursion in action. So let's start again with the addition example. Okay, so add, we're going to have add, of course this is a function from 2 inputs to a single output. Okay, so again with our primitive recursion, we have our f is our base case function, our g is our recursive case function, and we have our h, which is our resulting recursive function. In this case, of course, we want h to be our add function. So we know f is going to have 1 less input than the recursive function. So f is is a function which takes a single input and gives us a single output. G, we know from the definition of primitive recursion, is going to have 2 more inputs than that base case function. So it's going to be a function from inputs of 2 to a single number. Okay, so let's think about what we're doing here. We want add x, y to be x plus y. And add is going to be the primitive recursion, parameter 1 of f and g. So let's think about this. What do we want f and g to be? F is our base case. What happens when we do add of x and 0? Well, by the definition of primitive recursion, this is f of x. And we want this, what happens when we add x plus 0? Well, we just want this to be x, right? So we just want this to be x. So, and we know what this function is, right? F of x equals x. This is our identity projection again. And now let's look at the recursive case. So here, what's going to happen? We take add of x and some y plus 1, and primitive recursion gives us g of x, y, and add of x and y, right? And what do we want that to be? Well, we said before, we want this just to be the successor of add x, y, right? Because the sum of x and y plus 1 is 1 greater than the sum of x and y. Okay, so we're getting there now. So let's look at what G is doing. So let's abstract away all this stuff. So G is taking 3 inputs. We'll call them x1, x2, and x3. And its output is the successor of its third input, right? So we pump this in and it gives us the successor of its third input. Let me redraw that 3. Okay, so this looks like something achievable. Pause the video here to see if you can write down G as a composition of primitive recursive basic functions. Okay, so we see here that G is equal to the composition of the successor function and the projection function, which takes 3 inputs and gives us back the third input. So all in all here, we know what our f equals, and we know what our g equals. So what we're left with is that add is the primitive recursion with parameter 1 of proj11 and successor of proj33. Nice. So this is, we just defined addition in a world where addition doesn't exist. So I think that's pretty cool. Now I know what you're thinking. You cannot wait to define some more functions using primitive recursion, and I won't make you wait. Let's look at some more examples. Let's look at multiplication now. So multiplication, again, is going to be a function from inputs of 2 to a single output. Let's look at the primitive recursion thing again. So we have our f, our base case function, we have g, our recursive case function, and we have our h, our resulting recursive function, which of course in this case we want to be mult, because I'm going to claim that we can construct multiplication using primitive recursion. So again, f is going to be a function from a single input to a single output, and g is going to be a function from 3 inputs to a single output. Okay, so the game here is multiplication is the primitive recursion with parameter 1 of f and g. Let's look at our base case. Base case is mult of any number and 0. What's it going to be? Of course it's going to be 0. So primitive recursion, of course, is giving us f of x when we do this. So f of x equals 0, and we know what this function is, the function that we give it a single input and it gives us the output 0. That is, of course, the constant 0 function, which takes one argument. Now let's look at our recursive case. Recursive case. The multiplication of x and some y plus 1 equals g of x, y, and the multiplication. Let's move this along here. This is getting a little bit messy. And the multiplication of x, y. So the mult of x and y plus 1 is some function of x, y, and the multiplication of x and y. Okay, so let's take a step back and think about what this is going to be. So when we do a multiplication like 3 times 2, how can we express that in terms of 3 times 1? Well, that is 3 times 2 is 3 times 1 plus 3, right? So mult of x and y plus 1, we want to equal mult of x and y plus x, right? Okay, so that's what we want our g function to return, our recursive case function. And we see here that this is the addition. So g takes 3 arguments, we'll call them x1, x2, and x3. And it's giving us the addition of its first argument and its third argument, right? x1, x3. So again, pause the video here and see if you can write this down as a composition of the functions that we've already defined. Okay, so g as a composition, we describe this as, what's the outer thing here? It's add, and we've already defined add on the previous example. So we're going to say add, and we're composing that with the thing that takes 3 elements and gives us the first element, which is of course proj 3, 1, and the thing that takes 3 elements and gives us the third element, which is of course proj 3, 3. Cool, so now we have our f and our g. We can say multiplication equals the primitive recursion with parameter 1 of 0, 1, and addition composed with proj 3, 1 and proj 3, 3. Neat. Okay, let's look at another example. We'll look now at the example of predecessor. So predecessor we want to define as kind of the opposite of the successor function. So the predecessor of x is x minus 1, and obviously we can't say predecessor of 0 equals minus 1, so what we'll say instead is the predecessor of 0, we'll just sort of cut it off at 0. Okay, so let's see how we can define this using primitive recursion. So predecessor is a function from, of course, one input to a single output. So we're going to have our f, our g, and our recursive function h, which is going to be, in this case, our predecessor function. So f is going to be a function from actually 0 elements, inputs, to a single output. Now this 0 might look a bit scary, but I promise it works out in the end. And g is going to be a function from 2 inputs to a single output. Okay, so let's define this as the predecessor function is the primitive recursion with parameter 0 of f and g. And let's look at our base case. The base case is predecessor of 0 equals, of course, f of no inputs. And we want that to be, as we defined up here, we want that to be 0. So f is just going to be the 0 function which takes no inputs. Now let's look at our recursive case. And here we're going to have the predecessor of sum y plus 1, and that's going to equal g of y and the predecessor of y. And what do we want this to be? Well, the predecessor of y plus 1 is of course y, so we just want this to be y. And now it's pretty clear that g is a function that takes two inputs, x1 and x2, and it's just giving us back x1. So of course g is proj 1, 1, and now we have defined the predecessor function. As easy as that. Nice. So I'll leave you with a couple of challenges here. See if you can define the following functions. So we want to define subtract, which is a function from two inputs to a single output. We'll define this as a total function where we want it to be x minus y, but of course x minus y might be a negative number, so if it's a negative number, just return 0. So let's express that here as the maximum of x minus y and 0. So if x minus y is less than 0, just return 0. See if you can define that as a primitive recursive function. And see if you can define this function is 0. So is 0 is a function from one input to one output, and is 0 just returns 1 if x is 0, or 0 otherwise. Okay, so what we've defined so far is these three building blocks, these basic functions, and we've also defined these constructions, composition and primitive recursion. And with those, that's actually all we need to build the set of primitive recursive functions. So anything that you can build using these basic functions and these constructions is in the set of primitive recursive functions. And this set of primitive recursive functions is kind of a stepping stone on the way to the partial recursive functions. There's just one more construction that we add to allow us to get to those partial recursive functions. Notice that each of those basic functions is a total function, and each of these constructions preserves the totalness of the functions that go into it. So actually, the primitive recursive functions, it's worth noting, are all total functions. We can't define any partial functions using the primitive recursive functions, but the construction that we'll introduce next time of minimization will allow us to construct this set of partial recursive functions, and we'll see that we can define some meaningful partial functions using that. Cool, so that's the primitive recursive functions.